Okay, let's continue. Now, when two nuclei interact with each other, it can be either scattering or reaction. These are two different concepts, and mostly people confuse them. I mean, when you have, okay, like this type, elastic and inelastic scattering, when you say scattering, initial and final channels have the same nuclei. You see, A over target A, A is the projectile, capital A is the target, and the exit channel is the same, then it is called scattering. And it could be elastic scattering and inelastic scattering, where these stars denote the excited nucleus, like the example on carbon. Now, when you say reaction, in the reaction case, initial channel is A plus capital A is different from the final channel, exit channel. This is called reaction. Therefore, when you classify something, I mean, you should be very careful in terms of scattering versus the reaction. Therefore, either scattering or reaction, elastic scattering is always present. It always exists. Then it could be inelastic scattering or inelastic reaction. As you see, the initial and final channels are different. Examples are here. It could be radiative capture or photonuclear reactions, photofission, etc. Their gamma ray basically comes into the target, or it could be knockout type transfer reactions could also happen. There, the criteria is the Q value of the reaction. It could be positive or negative or zero. If it is zero, it is elastic scattering. If it is positive, then exo type, or if it is negative, it is endogenic reactions. Now, when you have a reaction, I mean, the observable is called actually cross-section, but what you obtain in the experiment is either angular distribution or excitation function. In the case of angular distribution, you have a well-defined energy, E, and the scattering takes through the angles located at different detectors at different angles. When you say excitation function, in that case, theta is fixed and energy is changing to observe. In theory, I mean, it is either direct problem, determine the cross-section from the potential. Therefore, it is like a two-body problem, it is called, or mean field problem. Or inverse problem, it's called determine the potential from the cross-section. These are two alternative ways. Now you have two nuclei coming to each other. There, I mean, since because of the proton at each nucleus, first thing, I mean, it will feel is because of the charge Coulomb field. Therefore, it should come and scatter like this. This is called Rutherford scattering or Coulomb field scattering. It could be elastic, and it is well known as Rutherford scattering. It could be inelastic, therefore it's called Coulomb excitation. But if the energy is high enough so that it breaks the Coulomb field and gets into the nuclear field, then it is surface or volume inside the nucleus, either shape elastic or what is called compound nucleus or resonance scattering. This is an example of Rutherford scattering. You see, this is this always takes place actually because of the charges of protons. We have always this Rutherford scattering, and as you see, it directly proportional to the squares of charges and inversely proportional to the energy, but the behavior is sine over theta, sine over the fourth, theta over 2, like this. This is well-known behavior of Rutherford scattering. Now, in the nuclear reactions, it could be either compound or direct reaction. Compound nuclear reactions happens at small impact parameters. It's mostly at very low energies, and it has 2 steps, never forget. And many of the radiopharmaceuticals are produced through compound nucleosis reactions. I mean, this is mostly called equilibrium reactions in theory, but you have this projectile comes to the target, and they combine and create a new nucleus called C, for example, C star. This is the excited state, and it decays into 2 different nuclei. Here it forgets how it is created. This is the theory, logic of the compound nucleus. Therefore, it forgets how it is formed and decays independently. Therefore, you can obtain many different types of radioisotopes or later radiopharmaceuticals. The time scale is very long. It is up to 10 to 18 seconds. And the cross section is very isotropic, very symmetric, around 90 degrees. Whereas the direct reactions, I mean, it happens at large impact parameters, very high energies, and it is direct. I mean, it's one-step reaction. Time scale is very, very short, 10 to the minus 22 seconds, and we have oscillatory cross-section. These are the examples when you have compound nucleus reactions. I mean, for example, a proton on aluminum, for example, at low energy, where they can get together, for example, and create a new nucleus. The cross-section is like structureless. It is like this compound nucleus form. This is the cross-section for compound nucleus. Whereas if it is direct at high energies, then it is mostly forward-peaked oscillatory structure. But when you have a transfer reaction, for example, proton, neutron, or alpha, then this cross-section here, instead of like exponentially decreasing, then it starts rising again. That indicates there is a transfer taking place. Now, the measurable, observable we measure is called cross-section for such a reaction. This is, for example, a nucleus projectile A comes on the capital A. This is the entrance channel. B is here the impact parameter. We should, we use same symbols, but this P is different from this P. That's the reaction product. This is what is called impact parameter. The distance of the projectile to the collision axis, scattering axis, basically. Okay. Therefore, this is an experiment. We should be very careful. I mean, this is a beam from accelerator. It's coming. This is the target. And this is experiment. In theory, we consider them as the projectile is a plane wave coming to the field. Target is called potential field. Therefore, the interaction of this and this are the same. Therefore, cross-section is like a probability of a reaction to take place or to occur. Therefore, what we have here is the number of targets here, the the scattered one into the solid angle is called RB, and N is the number of target nuclei, and I kind of incident particles A. Therefore, the ratio of them called cross-section, and the unit of cross-section is on the limit of area, of course, it is meter square, centimeter square, or 30 centimeter square. It is commonly called barn. One barn is 10 to the minus 24 centimeters squares, or 120 square. Please don't forget this barn or cross-section concepts. Now, this is like laboratory system, and the laboratory system, normally, what we have, this is projectile, this is target. E is the impact parameter, K is the wave number or energy. Now, before the collision in the laboratory system, there is always an energy and velocity of the projectile. And target is always at rest. Never forget it. Okay? In the laboratory system, now projectile coming to the target. Therefore, in lab system, we have always this projectile with a certain well-defined energy. Okay? Target is always fixed. And after the interaction, both are in the forward directions. Therefore, here and here, we put detectors, and we count the number of particles, we calculate the cross-section, we plot the angular distribution or excitation functions. Okay, this is the lab system. But we never solve this in theory in the lab system. For example, in your textbook, like modern physics, quantum mechanics, or electromagnetic theory, all lecture, you always use center of mass system in theory. When you say central force problem or two-body problem in your lectures, the Schrödinger equation or Dirac equation or Klein-Gordon, any type of equations you solve in physics are in center of mass system, not system. Okay, very careful. Therefore, in the center of mass system, what we do is, in theory, we transform this lab system to center of mass system. What we do is, we find the center of mass of the system, like the heavy one, then move it so that this moves on the opposite side, this also moves like this, and equal and opposite momentums, okay, like this. Therefore, the scattering takes in the reverse directions with same momentum. Therefore, the number of degrees are small so that we get more physics from this. Like this is the illustration, like this is projectile in the lab system, this is the target. This is fixed, and projectile comes and hits it. This is the collision in lab system. This is normal life, like this. I drop this. This is projectile, that's target. Okay, this has energy and it is fixed. Now, in theory, in your textbook, so far, the equations you solve, you never solved in the system. What we do is we transform it to center of mass by finding the center of the system, then change it to center of mass or kütle merkezi system. Therefore, we change the angles to center of mass and energy. Please don't forget that there is a relation between lab and energy center of mass energy system, momentums, angles. Therefore, remember this formula, okay, for the mass to lab system. Therefore, when you solve these equations in the quantum physics, for example, now you have this reference system. You have two masses, M1 and M2, and distances from the origin, okay? Now, what you do is you find the relative vector, these two positions, define the center of mass by using this formula, and write the Schrödinger equation for mass 1 and mass 2, okay, two masses, and this is the potential between these two. What you do is you do these transformations you already did in the past, probably, and by using the reduced mass equation, now what you obtain is the center of mass motion. It's a constant. The solution is the plane wave, and this is the relative motion. That is the describing the interaction of two particles. Therefore, when you solve the Schrödinger equation, for example, in third year quantum mechanics, or any type of equation, you have this two-body or relative motion solution. H psi equals E psi. Okay? Therefore, this is the one that you are solving with well-defined energy and position. Therefore, please don't forget that, you know, when you write Schrödinger equation, you are writing actually this one, relative motion. After all these separation of variables, you obtain this. And the center of mass, as you see, there is no potential. Therefore, there is just, it's the plane wave, e to the ikx or I. Is the solution. Okay, this is fixed. This is relative motion you are describing. Now, why is it important? I mean, I should repeat this. I mean, when you do theory, okay, it is called two-body problem or central force problem. Please check it from your textbooks, okay, quantum mechanics or modern physics or nuclear physics course. It is called two-body problem. Now, in order to describe interaction of, for example, this is proton and this is carbon, it comes to this one. You do experiment in the lab system, but theory is not, you know, done that. We have to move from lab system to center of mass system, right? By using simple formula. Now, separate the center of mass motion and find the reduced mass between these two masses. Then define potential and solve the Schrödinger equation. If you do this for nuclei, you are doing nuclear physics. If you are doing it for atoms, you are doing atom or molecular physics or material science, okay, or chemistry. If you are doing it for cells, you are doing biology, molecular biology. If you are doing it for, you know, leptons or quarks or others, then you are doing high energy physics, okay. Therefore, this is theory, and it is very simple if you understand it well. Therefore, this is the simplest way to explain it, okay? Yani anlamadıysanız bir anlatayım bir kez daha Türkçe, okay? Yani,
So can I ask something for?
Please.
We cannot see the whiteboard, so can you write it here also?
Yes, I will show you later. I mean, when you say force, I mean, we derive the potential from the force, as you know. Therefore, it is a kind of effective potential, let's say. It is sum of, for nuclear case, it is sum of nuclear plus centrifugal plus Coulomb potentials. I will show you, okay? Now, therefore, when we say, okay, this is experiment on the left, a particle projectile with an impact parameter B is coming to the fixed target. The result of this experiment is exactly same as this one. For example, a reduced mass M between two masses, you have a reduced mass M with energy plus the potential. Therefore, if the potential between two particles are negative, that means attractive. Okay, this is in that case we use square. But if the potential or force between two particles are repulsive, for example, two protons, then we use the barrier. Therefore, the results, the theory of solving this and making this experiment exactly the same results we obtain. Okay? That's why we solve these square band barrier problems, the simplest case in quantum physics. Actually, what they describe is the interaction of two particles with each other. Okay, that's theory. That's experiment. This is theory.
And is the angular momentum of
Yes.
coming? But the Schrödinger equation, does not account for the angular momentum.
Yes. Angular momentum, I will show you now. Effective potential, yes, but spin doesn't. Spin, Schrödinger, in the Schrödinger equation, we don't have spin. Yeah. But okay, let me show, for example, a more sophisticated one. This is like the effective potential here for different L values. L equals 0, 10, 20, 30, 40. Now, for L equals 0, there is no repulsive, but when L increases, you see the pocket disappears and it becomes completely repulsive potential. Now, let me show you this effective potential, maybe. Okay, this is like force or effective potential of two nuclei between two nuclei. First one is nuclear potential, like this form. Second one is the Coulomb potential between these two. Third one is the centrifugal potential due to the rotation of nuclei from F. Therefore, the sum of them, the sum of these three, gives you this potential. This one. For L equals 0, 10, 20, etc. For the sum of them. Normally, if you look at here, this is the nuclear potential, completely attractive, you see. This is the centrifugal potential, and this is the Coulomb. The sum of these three gives you this shape. And this is the describing the everything around this potential. This part creates the bound states so that nuclei are together, and this part is repulsive so that it is this binding or aparting the nuclei. Do you have any questions? Because this part is very important for theory. I mean, if you have any questions, you may maybe. Ege anladın mı? Tamam, sen tekrar bak ama burada yani bu kısmı bence bir Türkçe'de tekrar edeyim. Niçin önemli bu kısım? Şimdi bakın elinizde çevrenizdeki gördüğünüz her şey. Bu şu anki yaşadığımız sistem laboratuvar sistemi. Gözlemin yapıldığı yer. Tamam mı? Bakın burada her zaman gelen parçacık, mesela hanımefendi Hedef'e doğru gidiyor hedef bakın. Bu gelen parçacık o hedef. Bakın gelen parçacık hep bir enerjiye sahip, hedef hep sabit. Buna lab sistemi diyor. Tamam mı? Mesela gözlemin yapıldığı, bu işlerin yapıldığı, ölçümlerin yapıldığı her yer lab sistemidir. Mesela diyelim suyun içerisine bir damla bir şey bıraktık. Üretti. Gelen yine projektör belli bir enerjiye sahip vesaire. Hedef her zaman dur. Buna lab sistemi diyor. Bunu hiçbir zaman teoriyi, bunu tanımlamayı lab sisteminde yapamıyor. O yüzden kütle merkezli referans sistemine taşıyor. Kütle merkezinde anlattık. Şimdi dolayısıyla diyoruz ki eğer böyle bir deney varsa bunu teorik olarak tanımlamak istiyorsak bir, bu lab sistemindeki enerji, momentum, açı ve benzerini kütle merkezi sistemine taşıyoruz. İlk yaptığımız o, tamam mı? Şu. Sonra iki cisim var ya, bu iki cismin bunun gelip buna çarpmasını diyoruz ki sanki iki cisim tek bir cisimmiş gibi düşünüyor. Ona indirgenmiş kütle tanımlıyoruz. Şunu M1 çarpı M2 bölü M1 artı M2. Bu ikisinin bunların arasındaki kuvvete bakıyoruz. Dolayısıyla potansiyele. Biliyorsunuz kuvvetle potansiyel arasında F eşittir eksi gradiyent V değil mi? Gradiyenti potansiyeli. Dolayısıyla ikisi arasındaki kuvveti yazıyor. Mesela iki protonsa bu. Diyorsunuz ki Z1, Z2 E kare bölü 4 diyorsunuz. R diyorsunuz. Coulomb. O zaman o yüzden mesela kuantum fiziğinde ilk hidrojen problemini çözersiniz. Değil mi? En basit yani. Tamam mı? Hidrojenle başlarsınız. Dötörün vesaire. Şimdi dolayısıyla bunun buna çarpması deneyiyle iki cismin sanki tek bir cismin bu ikisi arasındaki potansiyelle yani kuvvetle yaptığı etkileşme aynı şeydir. Buna deney diyoruz. Yani şuna. Bunun bu alanla etkileşmesine, kuvvetle etkileşmesine ya da potansiyelle çözdüğümüz zaman bu teori oluyor. İkisi de aynı sonucu veriyor. O yüzden bakın kuantum fiziği falan yani şeye geçtiğimiz zaman teoride çözülebilen problemlerle başlarsınız. En basit problem karekök. Sonsuz kuyu. Efendim söyleyeyim, bariyer değil mi? İşte nedir? Harmonik osilatör. Coulomb. Niye? Çünkü bunları çözebiliyorsun. Demek ki siz şu problemi çözdüğünüz zaman şöyle düşünün. En kütleli, en enerjili bir parçacık 3 boyutlu zaten. Böyle bir kare kuyuya geliyorsa bu ne demektir biliyor musun? Sizin elinizde iki tane kütle var. Yüklü parçacık var. Bunların arasındaki potansiyel neymiş? Çekicilik. Ne? Proton, elektron. Bakın bu onu tanımlıyor. Anlaştık mı? Çekici çünkü. Yani proton, elektronu çeker. Şimdi diyelim proton, proton olsaydı. Proton, protonu ittiği için ya da elektron, elektronu ittiği için bu sefer ne çözüyorsunuz? Bariyer. Birbirlerinin itici proton. Bakın negatifse bound state'ler yapıyor. Bağlı durumlar yaratıyor. Yeni sistemler yani füzyon ve benzeri. Pozitifse itiyor. Ayrılıyor. Dolayısıyla siz 3. sınıf kuantum fiziğinde öğrenci olarak bir karekuyu potansiyelini çözdüğünüz zaman neyi çözmüş oluyormuşsunuz? Aslında sizin çözümünüz iki cisim birbirleriyle etkileşiyor ve bunların arasındaki potansiyel, dolayısıyla kuvvet çekiciymiş. Anlaşıldı. Siz bir 3. sınıf kuantum fiziğinde bariyer problemi çözüyorsanız oradaki şey neymiş? Sizin iki cisminiz var ve bunların arasındaki kuvvet ya da potansiyel itiyormuş gibi. Anlaştık mı?
Hocam, fisyon olayını nasıl değerlendiriyorsunuz?
Oraya geleyim. Daha da geleyim. Yani o da apart oluyor. Oraya da geleyim. O tünelleme gibi, tunneling gibi. Onu da anlatacağım. Yani dolayısıyla ama niye çözdüğünüzü anlaştık mı? Yani karekuyu mesela harmonik osilatörü Coulomb'u Bu teoride çözüyorsunuz. E üzeri artı eksi i kare buluyorsunuz vesaire. Bu çözümlerin hepsini yapıyorsunuz ya. Oradaki fizik neymiş? Sizin elinizde iki tane cisim var. Bunlar bakın ya bir araya gelirler ya da ayrılırlar. Bir araya gelenler çekici potansiyeller, atraktif potansiyel. Yani negatif, bu sürekli bir araya getiriyor. Bu niye kadar proton, elektron hemen hidrojen atomu. Tamam mı? Proton, nötron bir araya getiriyor, törün vesaire. Bu ama birbirlerini itiyorlarsa bu sefer de itici potansiyel olması gerekiyormuş. Dolayısıyla bu teorik fizik için çok önemli bir şey. Teorik fizik aslında bu kadar da basit. Bunu relativistik de yapabilirsiniz. Bunu işte atom fiziği yani mesela iki atomun etkileşmesini yapıyorsanız siz atom fizikçisi değilsiniz. Ya da kimyacı değilsiniz. Ya da malzeme fizikçisi. Siz teorik fizikçisiniz. Yani her türlü modellemeyi yapabilirsiniz. Yeter ki ikisi arasındaki bu kuvveti dolayısıyla potansiyeli iyi tanımlayın.
Yani şimdi
Buyurun.
ben relativistik durumlarda mesela 200 ml falan
Hı hı.
yaptığımızda ve spin durumunda da mesela Dirac denklemini benzer bir şekilde kullanabiliyor muyuz?
Tabii Dirac da sonuçta bunların hepsi mean field hocam. Ortalama alan teorileri. Ortalama alan teorisi dediğimiz şey şöyle
Yani
e,
Schrödinger denkleminin geçerli olmadığı domainlerde
tabii.
aynı
Orada
benzeri
şey,
şekilde
aynı mantık aynı. Klein Gordon'da olsaydı. Buradaki mantık şu hocam. Diyor ki bakın elinizde iki tane ya da daha fazla cisim var. Ama siz three body falan çok problemli, matematik olarak karmaşık koordinat sistemleri vesaire sorun olduğu için biz onlara hep iki cisim problemine indirgeriz. Yani bütün teorik kitaplara bakın, bütün kitaplarda hep iki cisim ya da central force problem diye bir kısım var. Merkezcil kuvvetler. Şimdi biz diyelim bu bir parçacık, bunu bıraktık, geldi buraya çarptı. Bununla iki atomun ya da iki hücrenin etkileşmesi arasında bir fark yok hocam. Ya da iki, yani şu an bu stok markette de uygulanıyor bunlar piyasaya. Aynı şey. Yani ortalama alan teorisi diye geçiyor. Deniyor ki bu gelen parçacık lab sisteminde her zaman hedef sabit. Bu gelir buna çarpar. Şimdi bu ikisini teorik olarak tanımlayabilmemiz için diyoruz ki şunla şunun indirgenmiş kütlesine bu. Sanki tek bir cisim gibi düşün.
yani ben şeyden ziyade
Sonra bu ikisinin arasındaki potansiyeli buluyoruz.
yani
Kuvveti.
geçerli olan domain, yani mesela Schrödinger denkleminin çözülebileceği geçerli domainler var.
Bunlar relativistik
ve
spinsiz.
O zaman Dirac denkleminin
Spin varsa
ve
bir geçiyoruz.
relativistik
Eğer fermiyon.
fermiyonsa
Yok bozolursa bu sefer Klein Gordon.
Evet.
Ya da Duffin kemer
yani
spektra.
gelen projektörün cinsine göre
Aynen.
evet.
Ama yine mantık aynı hocam. Mean field dediğimiz ortalama alan teorisine dayalı. Dolayısıyla bütün fikir şu. O yüzden teorik fizikçilerin hepsine bakın ya da birinci sınıf fiziğe başladınız kimyaya. Kuvvet dersiniz, bitersiniz kuvvet potansiyel, profesör olursunuz hala kuvvet potansiyel dersiniz. Çünkü bütün mantık bunu tanımlamak. İki cisim arasındaki etkileşme nedir? Bu sefer siz biyofizikte yapabilirsiniz, biyolojide yaparsınız, kimyada yaparsınız. Yani fiziğin her türünü yaparsınız zaten. Malzeme fizikçisi olursunuz. Yeter ki bu mantığı iyi anlayın. Yani aynı şey mesela şuna bir damla boya bıraktık. Yeni bir renk oluşturuyoruz değil mi? Bütün o bound state'ler falan değişiyor, özellikler değişiyor. Ama mantık ne? Yine iki cisim etkileşmesi bakın. Gelen bir cisim var, bir de hedef var. İkisi arasındaki mean field'ı yazıyoruz. Ortalama potansiyeli, kuvveti. Spinsizse hocamın dediği gibi Schrödinger'i çözüyoruz. Spinli ise işte relativistik ise diğer denklemleri çözüyoruz. Dolayısıyla bu teorik fizik. Tamam. Bak. Okay, let's switch to English again. Now, what is the effective potential then? I mean, how we describe? This is the main question of all theories. Chemistry, engineering, physics, mathematics. Therefore, the idea is to define the correct force or potential between two nuclei or two objects. Therefore, we know that when they are very, because of charge, they have this Coulomb repulsion, Coulomb force. We have, because of the centrifugal potential and angular momentum dependence, and L equals 0 is S state, L equals 1, T, B, etc. Okay, this is the centrifugal potential. And the idea is to describe correctly the nuclear potential. There are two ways to describe this nuclear potential. First one is the phenomenological approximation. Second one is the macroscopic one. Now, from the phenomenological approximation, we know the density distribution of a nucleus. Therefore, it is at very short distances, it has a very strong hard core, then it decays exponentially. Therefore, the formulation like this, it is target distribution, it is called, or Saxon type potential. It exactly fits this with 1, 2, 3 parameters. We can use this. I mean, it extends well. The other way is to find from the first principle. Now, we know that there is a charged particle here, for example, a nucleon here. And we have another nucleon in the target or projectile. Therefore, we know this, the density of this. We know the density of that, and we know the interaction between these two, like Ikawa type interaction like this. And if we integrate all over the space, all neutrons, we obtain the microscopic potential. It is called folding potential. And the shape is like this, you see. When there is no Coulomb and centrifugal, this is the nuclear potential. As you see, it is negative, therefore it is binding protons and neutrons together here. But when there is the effect of Coulomb and centrifugal, then it creates this pocket. Now, this shows that, you see, goes to infinity. Therefore, two nucleons, I mean, two proton or two neutron or one proton, one neutron cannot touch each other. Therefore, this is like a barrier. And this is the energy levels that are located here. Therefore, this is like a bound state up to 0 here. Here, for example, you have this uranium or carbon or whatever. You see, depending on speed parity levels, there are neutrons and protons are located here, as I showed in the first lecture. Therefore, this is the Coulomb barrier, of course. Now, in order to classify the physics, I mean, we should first define what is the Coulomb barrier. Because first, we should cross the Coulomb barrier in order to interact with the other nucleons. Okay, this is the approximate value of the Coulomb barrier. R is the R0 times A⁻⁴. And at very low energies below the barrier, there is tunneling. Therefore, there is reflection, transmission coefficients. Probably in third year quantum physics you did. Therefore, nuclear astrophysics studies are here at very low energies, like Big Bang and, abundances of nuclei, nucleosynthesis processes are described, this formula with this potential at low energies. Near the barrier above here, these are mostly optical coupled channels and other models are working here. This is mostly nuclear physics and related fields. And above the barrier, mostly it is very, very fast. Therefore, there is no partial wave expansion. It is mostly Glauber and classical scattering, actually. Therefore, now you solved, for example, in third year quantum physics. This is like a well problem, infinite well problem. Now you obtain these wave functions and you obtain these energy levels. Now, okay, now this is exactly describing the kind of nucleus. Therefore, don't underestimate third-year quantum mechanics. Okay? It is very, very useful tools to show you how it is used. This is like when you have attractive potentials, for example, like this one, you have these eigenfunctions, wave functions, ground state, and excited states, and square of them, so that it gives you the probability of finding those particles and energy levels. Now, why is it important? You see, it is third-year quantum mechanics problem, but it produces you these semiconductors, for example. See, I mean, it is the driving force for the technology now, all these semiconductors. Therefore, it is a kind of doping, and you describe it with a simple quantum mechanical solution. And it is very advanced level production in technology, but it is a very simple way of solving it. That's why it is important that you should do this doping and other things, or well understand how this two-body problem is working. Same as step potential, you already did all these in the third-year quantum mechanics. I'm sure you did it, and you find these reflection transmission coefficients, and exactly you see the number of transmitted ones give you the cross section. You see, this is like I mean, simple quantum physics, but you obtain exactly the experimental observables you already did in third-year quantum. For example, what is fusion when you say? Fusion means, this projectile comes and, absorbed by the target. What does it mean? There is no transmission. This third-year quantum mechanics is so powerful if you use it correctly. And it is so easy to describe very, very well sophisticated examples. Okay, okay, I am on time. Now, this numerical solution, now, like people like me, I mean, we use the Fortran languages. Therefore, we are very old generation. Now you are using artificial intelligence, therefore much easier, therefore numerical solutions. I mean, it is a kind of iteration method. We solve the Schrödinger equation iteratively, but better ways, there are different ways. I mean, we showed you simple Schrödinger approximation, but there are integral equations, like if we call this Hamiltonian as L, so that we obtain what is called Born approximation. It is like a green function similar to that one. What this says is very simple, actually. You see, you have an incoming wave and scattered wave due to this target or potential field. Therefore, we have initial wave affected by a potential and outgoing wave. Therefore, if we integrate it, it is called Born approximation. It is very simple, and the square of a theta scattering amplitude gives you the differential cross section. Integration of it is gives you the total cross section. Now, this is if you have more than actually one potential, what I mean, there is this potential, for example, a particle is coming, hitting the target, and passing through. Therefore, this is the initial wave function affected by the potential and this is the scattered one. Okay. Now, for this one, this is now incoming one, and this is the potential field, and this is the outgoing one. So that you can iterate it more and more, like a elastic scattering plus inelastic scattering and other transfer processes. This is called Born approximation. It is very simple and effective way. Therefore, please solve this example. For example, we have a Yukawa type or similar Gaussian potential. Scattering amplitude is very easy to find. There is this potential and sine squared. We showed here how to obtain this sign for the elastic scattering case. I didn't show, but probably it will be homework for you. Okay. Then this is the potential and this is the cross section roughly. I mean, easy way to find. Therefore, this is a homework for you for the future. Now, the second way we use is more accurate one is the partial wave expansion method. This is like a potential field. It has energy, wave number, and centrifugal term. Therefore, we obtain here for bound states a discrete spectrum. For the scattering states, for E equals greater than, 0, we have this continuous spectrum for positive energy cases. There we obtain this S matrix, what is called scattering matrix, or phase shift. I will show you now what is phase shift, and obtain the cross section with this formula depending on angular momentum L. As you see, it is again easy. Total cross section is the sum of elastic and reaction cross sections. Let me show you here the Bessel functions and Newman functions, regular Bessel and Newman. As you see, Bessel function starts from the origin, whereas the Newmans diverge to the origin at large distances. Now, this is the important part because when we have potential, as you see, negative potentials create this bound states. For example, proton and electron, they get together and create hydrogen. This is the potential that we use, okay? It is creating bound state. Whereas if there is a scattering like proton on proton and they scatter, that's repulsive potential. Therefore, imagine you are a plane wave, okay, free wave. Like your movement will be like this, you see, in the space. Whereas now, when you have a potential here, you see, you come and your phase will be changed. It's created by this potential. You see, it would be, this is that of blue one is the without potential, okay? No potential, free wave. It is. And when you have this this is the free wave, blue one, okay? Without potential, you see. Therefore, phase shift is 0. Now, when you have this purple one, that is when the potential is positive, negative here. Therefore, this free one minus this one creates you the positive phase shift. Okay? E to the this I delta gives you the S matrix. That S matrix gives you the cross section. Now, when you have positive potential, That means, like it is repulsive, then you see this one minus this one gives you negative phase shift. Therefore, when you have a repulsive potential, you get negative phase shift, and you have a negative or attractive potential, you get positive phase shift. This phase shift is very, very important. R, KR,
No, it's excess.
amplitude,
Um,
yes, amplitude. Like
um,
A sine KR, for example. A wave function, basically, it's a wave function, like sine KR minus L pi, okay? It's sine KR, for example. Therefore, we are neglecting A. Okay? This is a wave function, basically. Or e to the A I K R, if you consider that. Okay. Now, this is important. Yeah. Yeah. If you look at, for example,
Transition.
Yeah. Therefore, that one you get pulled up into S matrix because S matrix is related to the phase shift. Plug that phase shift here, you obtain the S matrix. S matrix, and you use that to obtain the cross section. Now, this is getting more sophisticated now. But if you are time, I mean, I can skip. But these are if you are going to do theory, either in chemistry or any type of theory. In physics, you should know this non-locality. Okay, resonances. All these iterations. I mean, this is called mostly absorption because when you send a light onto this one, or even a projectile, a photon, then some of them are absorbed or lost. These losses called imaginary part of the potential. But let me skip this part. It gets more sophisticated, like coupled channels. Therefore, one channel is coupled to other channel. Then the formations, of course, gets into play, like spherical one, oblate or prolate structures. And finally, you get this, basically. The force or the potential between two nuclei for different L values. And this is the absorbed one. For example, 6 helium on lead at 18 MeV. The potential is like this. Therefore, what happens is 6 helium is sent to lead at 18 MeV. Okay, we obtain a cross section. Now we theoretically describe it, or the imaginary part absorption again described. And this is the result, for example. Those are experiments. Dashed ones or solid ones are the theory. You see, this such a simple approximation, like two-body approximation, describe such a sophisticated and complicated problem so well, actually. This is for different reaction on nickel and lead. This is, for example, carbon. This is experiment. Dots are experiment. Solid lines are theory. As you see, quite well, actually, it is explaining. It's such a simple Schrödinger equation, but the results are really impressive that it takes space. Therefore, between theory and experiment. Now, what people are doing are actually, they are increasing the nuclear metal more. Normally, I mean, this is classical view of nucleus. Protons are, neutrons are very packed, strongly packed in a 10 to the minus 15 meters. Whereas now, by adding extra neutrons, mostly, they create this exotic nuclei. These nuclear radii are much larger than normal nuclei. Therefore, this is a very exotic field. These are called either Borromean nuclei or exotic nuclei or similar. Therefore, imagine this is that you have 208, around 210 protons and neutrons here, but it has the same radius as lithium. Here you have 210 protons and neutrons. Here you have 11, and they have almost the same radius. Therefore, this field opens us a new window actually to create exotic nuclei and new nuclei, new applications, medicine, etc. It's a very, very important field now, currently, very hot topic now. Yeah, please.
For example, so we talk about three different kind of potential. First is nuclear potential, the other one is quantum stepping potential, and the third one is the angular momentum.
Yes.
So we can basically say that the nuclear potential is more or less stability, the binding energy of a nucleus, right? So that
Yes.
each nucleus has a potential.
Oh,
That.
that's the binding.
Yes, and when we collide with a particle to this nucleus, then we will have a quantum scatter potential.
Now, no, you have relative potential. This has
Yeah.
potential, that has potential, then it becomes two-body problem.
Yes,
Then you have relative potential between these two.
these two, and the necessary potential of this relative one is kind of a quantum potential. I mean,
Effective potential.
effective potential,
Effective.
yeah, okay, sorry. And
It is
Yeah.
some of them, nuclear
Yeah.
between these two, plus Coulomb
Yeah.
between these two, plus centrifugal, so that in the center of mass, they will take.
because of the molecule. So this is an analogy of thinking of this way.
Yeah, therefore, this is the physics actually. Yeah, I mean, what I mean is, you see, here you have this projectile A hitting at target A, okay? And here, at the angle reaction, you put here detectors, okay? You measure this A and A, whatever.
Yeah.
This is an experiment, but we never do this in theory. In theory, what we do is we obtain this reduced mass because of these two. Okay. Then we write the force. Therefore, it is a gradient of VR, okay, potential. So then we obtain the potential like between these two, like let's say the nuclear, the Coulomb, plus the centrifugal, and solve the Schrodinger equation. This experiment and this theory, they give the same results. Okay, this is the theory, this is the. Now, imagine you are a material scientist and you would like to see the doping of proton on aluminum. What we do is very simple, proton plus aluminum experiment, okay? This is now experiment. Beforehand, you do simulation or theory, prediction. How? What you do is, okay, you first find the reduced mass of proton and aluminum, like this, and aluminum and proton divided by and proton plus aluminum. Then you write the potential between these two.
In order to understand how much energy you should.
Yes. Then solve the Schrodinger equation. Now, this is experiment and this is theory. These are the same. That's why in terms of quantum physics, we solve this parallel potential barrier problem. and harmonic oscillator, and okay? Because these are the ones that we can solve by hand. But never forget that that barrier problem or that well problem describing the interaction of two bodies, two objects, okay? Or two atoms. Therefore, if you understand the theory, you can do everything, like biology, chemistry, engineering, everything. Because this is the basics of theory. Okay, I think it is enough. I mean, it's tired. I'm not tired, but probably, yeah. If you have any questions, please don't hesitate to ask me. I am also staying at Yükseliş guest house, dormitory, whatever. And you can ask me anytime. In the afternoon, I will be presenting you the what if these nuclei are unstable? That's radioactivity, okay? In the afternoon. Okay, thank you very much.